A good robot actuator is much more than just a motor. It allows the precise control of limbs in many useful ways, like with these actuators I can actually change the mechanical properties of my robots just by changing a few settings. Right now you see them very springy and loose, making the robot very compliant and safe to work with. But by changing a few settings, I can also program them to be super stiff. The target position hasn't changed. In both demonstrations, the robot is trying to go to a standing position. But now that I've adjusted its settings, the joint almost feels solid, as if it were made from a rigid kind of plastic, not at all what you'd expect from a shaft on a bearing. But it is a revolving joint, and I can tell it where to go. If I control it with my remote, you can set the position very precisely. This encoder measures 160,000 steps per revolution, so in theory you could rotate it by 2,000ths of a degree. So I can move the arm fast, but I can also move it pretty slow. By now you may be wondering, what even is this robot? Well, I designed the Acrobot to perform human-like acrobatics. It has very few joints, no knees or ankles, no wrists or elbows, just single axes, hips and shoulders. But I did want it to be strong. Acrobats, who are very strong, may be able to do a planche handstand. So this became my goal for the Acrobot. It needed to do a planche. I guesstimated how much torque I needed and I gave myself a safe margin. These motors can push up to 25 Nm, but as you can see on screen, even if the robot is being shaken around a bit, it maxes out at only around 11, giving me plenty of headspace. I'm streaming these values from the robot to my laptop, but we also try to film them on the display of the robot. I've been doing planches for a few minutes by now, and this got the actuator so hot that it shut itself down. And I'm glad that these kind of safety features are built in so that the robot wasn't harmed at all. A few seconds later I could just boot it normally again. Now with all this torque and position data coming from the motors, you can actually use them as a sensor. And this means I can create some interesting control modes. For example, this is what I call Mannequin mode. The motor tries to stick to a certain position until the force goes over a certain threshold, and then it updates its target position to the current position as being read by the encoder. There is also this bilateral telepresence mode. I can control the right arm by moving the left or the left arm by moving the right. The formula for this comes straight out of the MIT paper that first popularized these kinds of motors, but I haven't fine-tuned the feedback parameters, which is why it's responding in such a springy manner. All these features together allow me to create performances and animations for my robot. I need the Acrobot to be strong, precise, but also a bit compliant. It needs to be durable and reliable, and I'm asking a lot from it. Sometimes my own code lets me down and the robot doesn't behave as I expect, but so far I've had zero issues with these actuators themselves. During shows I don't push the motors to its limits, and the software that I wrote also prevents me from accidentally doing so because I don't want anything that they attach to break. But even in this setup, the robot is pretty strong. I tried to make a jump, which shouldn't really be possible without knees and ankles, but it kinda works. And as you can probably tell from my face, I was surprised by this myself as well. So in the studio I was able to show you a lot of things that we can do with the robot, but then I also wanted to show you a few things with the motors that we can't do there. For example, how fast they can turn if I don't have them attached to something, because if I have the arm spinning full power, then they usually break off. There's actually a lot of things that I don't ever do at full power on the robot. But first of all, I'm controlling it in a different way now, because I'm controlling it from my computer. On the robot, I was controlling it from this module that I made. It's an ESP32, that's the controller, sending its information to a CAN transceiver, because these motors communicate over the CAN bus, and then you also need, in the ESP case, a logic level shifter, and I will show on screen whichever CAN transceiver this is. People always ask. I'm using ESP32, but you can use any microcontroller like a Raspberry Pi Pico or an Arduino board, or even, hey, where did my Raspberry Pi go? I had a Raspberry Pi here, but it moved over there. Anything that can control something can probably control the CAN bus through a CAN transceiver. But now it's running from my laptop through this USB device that CubeMars made that sent out a CAN bus signal, and then I power it from a battery. Of course you can use bench power because I have electricity coming from the wall, but because it uses so much power, most of the time these bench power supplies are not powerful enough if you want to push on something, so then the battery is much easier and you can just connect it with a battery connector. I'm controlling the motors now from the software that CubeMars made specifically for these motors, because they all have a different kind of protocol, but it's a really nice way that you can test this whole setup. On the robot I always use position control, where I set a position, but you can also run them on a speed control, where you just set a fixed speed and then it will keep on rotating forever. And yeah, on the robot it's not really practical because the legs, they only go so far, but just to give you an idea of how fast they can go, let me set the speed a little bit higher. This is not the maximum speed, by the way. Turn it off because the noise is a bit annoying. This maximum speed is very much controlled by the voltage of the power source, and I'm only sending it like 24 volts maximum, but these motors are rated for 48, so if you put 2 batteries of these in series, you would actually get twice the speed out of the motors. The torque is independent of the voltage, but the speed is dependent on the voltage, so you get a faster motor if you get a bigger battery. Let me tell you more of the control software. In this case I'm using the CubeMars tool that is specifically made for these motors, but it's a way that I can analyze what's going on. I already showed you speed control, but there's also position control obviously, so I can set the position to 1 radian. It will rotate a little bit, and it will depend how much force it will use to rotate to that point by its inner control loop, depending on these P and D values which are exposed from the PID loop that it's using. If you set a little bit more powerful, it will get closer to the actual position. Manipulating those values is how I was able to go from a very springy robot to a very stiff robot. So when it was very stiff I had this at a very high number, something like that, and now I can't rotate it by hand anymore. Whereas if I set this at a very low number, like I had this at 1 before, then I'll still be able to rotate it a little bit, and it is so powerless at the moment it won't even jump to its own position. I never use the maximums that it can go to, but it can get really stiff. If you need stiff and precise control, and instead of MIT mode, they recommend that you use servo control. And in the servo mode, there's many more variables exposed that you can control, like speed, but you can also have a torque mode where you set a constant amount of current going towards the motors. Or I don't even know what all these are because I never use this. I use MIT control. MIT control is designed so that as few variables as possible are sent over the CAN bus, which allows for very quick response times and not flooding the CAN bus, which allows to use the motors as a sensor, which is where you read data. For example, like you already saw a little bit of this maybe. Let me turn off the power at all. So now if I spin it by hand, no, I didn't turn on the power, of course. I had the power here. Pop! Now there's no power going towards the motor. And I can spin it by hand and you see the encoder value going up and down. Or there's the current value. Well, there is not much current going into the motor, but it's still breaking a little bit on current. The current relates to torque, like you can calculate torque from current. And it's sending temperature at all times, but because I'm not using it so much, it's at a very cool 21 degrees, it seems. So these kind of motor modules with an integrated gearbox and an integrated controller and the kind of software that allows you to control over the CAN bus, they come in many different shapes, sizes and forms. I'm using the ones from CubeMars and I'm very happy with them. I also get them partially sponsored, so that allows me to do this kind of artistic project. I compared a lot of motors before I started and these were definitely the best for me. But not all of them are the best. I mean, there is different types. So I started out with the AK7010 and I switched now to the AK88, and the reason for that, they're very similar in specs. Like they have the same amount of torque, almost the same speed. Actually the AK88 is a little bit slower. They're a little bit thinner, the AK88, but that's not what I got them for. There's 2 benefits to them for me. For starters, they have different size holes for attaching something like my robot arms. These are M3, these are M4, and I had some holes wearing out. They're tapped in aluminum, so if you have to remove arms very often, which I did because I poorly designed them, then they might wear out. But more importantly, there's an encoder in here which will tell you the position of the arm of the outside axis, but the encoder is only on the input shaft. So it goes through the gearbox, and then after the gearbox on this is 1 to 10, so then there's 10 different positions that the arm could be in, which you then have to calibrate first before you can do that. We wrote a calibration sequence on the robot and it works fine, but to save me from having to do the calibration every time I boot, I switched to the 88, which has a second encoder on the output shaft. Thank you for filming, Milu. Thank you for watching, and I hope you learned something. Bye bye!